very much.
Well, thank you very much, and I appreciate the organizers for involving in this wonderful event. I'm very impressed by the presentation given by Professor Weber, and that's something we really we are using the technology or using the phenomenon for our advantage, but we still don't understand the theoretical backgrounds of the use vibration modes to control to benefit from control in the material growth. So as introduced, my name is YONGFENG Lu at University of Nebraska Lincoln. I'm going to talk about laser-assisted growth of heavily doped diamonds with high crystallinity. Basically, we have to use laser to vibrate the precursor molecule to gain the crystalline diamond growth. Just this is the table of contents for the sake of time. Skip this one, and then the background. I think first of all, boron doped diamond and nitrogen doped diamond. So diamond is very special material. Everyone knows about diamond, but there is more and more, I think, needs in using diamond electronically. So one is for power electronics, because now we are going to like 5G, 6G in communications. We need the device to handle high frequency and high power, and diamond is a great material for electronics. But the problem is that it's diamond. It's very hard to dope diamond. Once you dope the impurities of diamond, the diamond crystallinity will be damaged, and they get probably non-crystal diamond, which is not good for electronic applications. So another application for boron doped diamond is that it can be used for electrodes to electrochemically or electrophysically kill the bacteria and the virus in water, which is important for environment protection, because we cannot before we release to the environment. Otherwise, there's a secondary contamination. So we try to use electrochemical approaches to disinfect the water. But the problem is that we need a diamond electrode, because it gives us the stability and electric conductivity, and also the right match with the chemistry involved in the water disinfection. And so in the past 15 or 20 years, what we have been doing is we are growing diamond in open air. So we use a combustion flame, and at the same time use a CO2 laser, which is a wavelength tunable. We can tune the vibration, the wavelengths of the CO2 laser to specific vibration modes of molecules to control the chemical reactions and to gain the growth rate as well as the crystallinity. So using this approach, we can get a crystal diamond, and sometimes we can get a very large diamond crystals in terms of millimeter. So it takes time, but this approach is much faster than conventional CVD process. So the vibration excitation, I think this is the approach we use to control or to improve the diamond growth. And so we have, in terms of chemical system, we have different system energy levels. Can be translational, can be rotational, can be vibrational, and it can be electronic. Certainly, electronic excitation probably more effective in countering chemical reactions, but usually the lasers in visible or UV ranges are more expensive, and also the powers are not very high. So we use the molecular vibrational mode because we can use CO2 lasers. The CO2 lasers can give us a very high power, 2 kilowatts, and also certain level of wavelength tunability. And so what we are trying to do is to pump the photons from CO2 lasers to vibrational modes of molecules. And so we believe that we use this one, we can drive chemical reactions to chemical dissociation of certain bonds with more like a favorable selection of bond breakings. Certainly, there's a lot more things we need to figure out, need to learn, and I'm glad that we have scientists like Professor Weber working on the basic science of chemical, the molecules and chemical reactions. So what we did was to look at how the laser excitation of different vibration modes are meaning to the chemical reactions. So we use optical emission spectroscopy or using open air mass spec to look at chemical reactions and what are the products being produced, what are the intermediate states that are being promoted by the laser excitation. So, for example, these are the 4 bands are the wavelength bands from CO2 lasers, from CO2 molecules. We can generate the 4 bands in this Bragg curve, and then we can resonate, for example, the wagging mode of ACM molecules at 10.532 micrometer at this point, or to ammonia molecule. So 4 bands give us some accessibility to the vibration modes of precursor molecules. And so one example is that we can excite the vibration mode of ACM molecules to enhance diamond growth. So in this combustion flame, we use oxygen and use acetylene in chemical reaction. The precursor of the ACM molecule has a one vibration mode at 10.534. And then this is the absorption spectrum of the ACM molecules, and it has the vibration mode. Unfortunately, the animation doesn't work well here. Basically, the 2 carbon atoms and 4 hydrogen atoms, they vibrate in opposite directions, and they call it the wagging mode. And we can see the absorption, which corresponding to the this ground state to the excited state, which is at 10.532 micrometer, and we have this resonance peak. And even if at the in the flame, the combustion flame, and so still there are quite a portion of the ACM molecules which are not burnt, not decomposed. So we can use laser to assist this process. And so there are different density of states at different rotational states. So we need to match this, we call the on-resonance of frequency to have the best resonance. And you can see that, when we tune the laser wavelength to 10.532, and we can see that the crystallinity improved a lot. Actually, the growth rate also improved a lot. And we just need to tune this wavelength slightly away from the this resonance, and you can see that the both growth rate and crystallinity will drop quite a bit. So this and we also control the same amount of energy being absorbed by the flame. So in terms of thermal energy, the energy pumped into the system is the same, but when you have different wavelengths, their effect is totally different. And for the growth rate, so if we have no laser, we have like 7.2 micrometer per hour, and now if we have the excitation, then we can have the growth rate a few times higher, 5 times, 6 times higher. And in terms of the volume rate, probably it's even much higher because this is kind of like a linear enhancement, linear deposition rate. So, if we the resonant excitation, the diamond quality is the highest, and you can see there's a one called a quality factor, which shows the sp2, and sometimes we also have like a amorphous carbon diamond. So when we have resonance, we have more sp3 diamond bonds in. One is the if we turn on the laser, you can faster. So we can see that when we have the resonance, the flame is the brightest. Side, and we can see from optic emission. And so if we look at the temperature of the molecules inside, so if you look at the CH rotational, have the on-resonance resonant vibration. We can see that even if we have the same amount of energy coupled into the system, but the chemical reactions are different when we tune to different wavelengths and to tune into different vibration modes. Okay, and we can also observe that when we tune to different wavelengths, the chemical species in the flame, they're all different. These are the mass spectra we measured using the they are okay, so that's a quick summary for this portion. So we can use growth, so we can have a much faster growth when we, and then we use this method to dope nitrogen in delicate material. Once you have doping, usually crystallinity will disappear. And so here we use ammonia as a source of nitrogen. And if you don't have anything, like if you don't put ammonia, usually get. But if you adding a little bit of ammonia, the crystallinity will disappear. And what you got is like probably nanocrystal diamond, or amorphous diamond, and you cannot get a high quality diamond crystallinity when you have nitrogen doping. And so what we did was to use the CO2 laser to resonate the ammonia molecules instead this time, and we find one ammonia wagging mode, which matches the one line of the CO2 laser emissions. So this is the instead of ethylene, we put ammonia here, and also shine the laser with a wavelength of 9.219 to match the wagging mode of the ammonia. And again, so it's similar as we did to resonate ethylene molecules. When we have a resonance, we see the flame becomes shorter and brighter reflect the more active and faster chemical reactions. And there is one strong resonance for the ammonia molecules at 9.219. Now, as we just mentioned, so if we don't use laser resonant excitation, the diamond crystal will drop in, will be reducing to like a amorphous or nanocrystal. You won't get a high quality crystallinity as we obtain in the pure diamond growth. So what we can do is, if we use resonant excitation, and at 9.219, you can see that the diamond crystallinity comes back, and with good diamond crystal structures, and also it has very high the doping level up to 1.5 times 10 to the 20 atoms per cubic centimeter. So similarly, we did the same work to dope boron into diamond, because we need both p-type and n-type diamond crystals to form device structures in diamond electronics. So what we did was to vibrate a precursor pH2 produced by the combustion flame. So again, we use oxygen and acetylene, and here we added H3BO precursor, BO3 precursors, and under combustion it will form BH2. Now we can tune the laser to 10.494 micrometer to vibrationally resonate BH2 molecules. And this is just the experiment setup to show that the CO2 laser is being used to resonate the BH2, and then we use OPO laser to look at different species in the flames to understand chemistry. And so there's one resonant frequency which is corresponding to BH2 here, and so we can see that there is kind of a peak we can match to excite BH2. And similarly, when we try to tune the boron rate, there's a the optimum boron concentration in the flame, and when you have less and more boron, and the crystallity will be worse, and there's a optimum boron rate. And then we started the chemical reactions using optical emission spectroscopy and laser interference to understand what kind of species are being produced by this combustion flame. And then we look at how the boron rate will affect the chemical species in the combustion flame. And so now with the resonance at the 9.4 something, is to correspond to the BH2 molecules. So we can see that when we increase the laser power absorbed by the flame becomes brighter and becomes shorter. That means that the energy is being used to promote the chemical reactions. And now we can see that with the laser excitation, the crystallinity can be improved very obviously. You can see this one is with no laser excitation. This one with laser excitation at 21 watt. You can see crystallinity is much higher. And also, the growth rate is promoted from 25 micrometers per hour to from 35, although probably the growth rate, it doesn't really change a lot. And the boron density is very high, and we can go to the level of 10 to the power of 21 to 22, which is extremely high, and we can achieve this kind of doping level with thermal diffusion, for example. And also we can get a very low electrical resistivity because the improved crystallinity in the diamond films. And this just shows the difference at the commercial BDD. We can probably come to the 10 to the power of 21 for the growth by this method. We can improve the doping level by probably 10 times. And also, we can see that the temperature dependence of resistance of hole density and also the hole mobility, they shows that this is a very much like a kind of like a P-type semiconductor. So it can be used for device fabrication. And then we use this for glucose oxidation, electrochemical reaction, and basically the BDD produced by our method has a very high electrochemical performance as compared to commercial ones. Okay, just a quick summary that we can use laser excitation to resonate the vibration modes of precursors and to enhance diamond growth and to improve the crystallinity. At the same time, we can also achieve higher deposition rate and better crystallinity. And also one topic I didn't mention is that actually we can control the growth orientation of diamond. We can use this method to control whether we can get a 1-0-0 surface or boron doped diamond to get a high doping rate and high crystallinity. So with this, I'd like to thank you for your attention. And so there's one paper regarding the how to use laser vibration excitation to dope boron in diamond. Thank you for your interest.